Okay, the last problem, and happy to report this is not the hardest problem. Thank goodness. Okay, it's not so bad really at all. Okay, so consider the complex numbers z1, z2, and w is equal to the quotient of these two puppies. So we're going to find the quotient by expressing z1 and z2 in modulus argument form. Okay, that's polar form. So if we change these to polar form, then it's really easy to divide them. In an earlier problem, I actually changed them to exponential form in order to divide them, but polar form is fine. Also, it works just as well to do them in polar form, but you definitely don't want to try and divide when they are in rectangular form. It's just a pain. So that's why they're asking us to change them to polar form. So polar form, we need to find our modulus and our argument. So for z1, we have z1 is equal to 1 plus square root of 3i. And I could do this on the calculator, but then I'm going to get decimal answers. And if I do it this way, if I do it by hand, which is what I'm about to do, then I'm going to be able to get exact answers. Okay, so the modulus is going to be the square root of a squared plus b squared. And so 1 squared is 1, square root of 3 squared is 3, 3 plus 1 is 4, square root of 4 is 2. So the modulus is 2. And then to find the argument is going to be tan negative 1 of b over a. And hopefully you're getting used to seeing this. The tangent of square root of 3 over 1 is equal to pi over 3. This is from the unit circle, so let me do a little sketch of the unit circle over here. If I want a square root of 3, remember tangent is sine over cosine, okay, because it's going to be y over x, okay, opposite over adjacent. So I'm looking for a sine that has square root of 3 in the numerator, so that when I divide it by the cosine, I'm left with the square root of 3 in the numerator. So that happens to be at pi over 3 because it is 1/2 square root of 3 over 2. So square root of 3 over 2 divided by 1/2. You would change that to multiplying by the reciprocal. Those cross out, you're left with square root of 3. So if you haven't got this memorized yet, it's not a bad one to be familiar with. When you're looking for the inverse tangent of the square root of 3, it's pi over 3. And if you're looking for 1 over the square root of 3, it's pi over 6. Okay, so there is our argument. So if we write this in modulus argument form, z1 is equal to 2 cis pi over 3. Okay, and in modulus form, write down the modulus of w. Okay, so I haven't gotten that far yet. All right, so now I'm going to rewrite z2. z2 is 1 plus I. So again, I'm going to find its modulus, square root of 1 squared plus 1 squared, because the coefficient of I there is 1. So 1 squared plus 1 squared, that would be square root of 2. And then the argument is going to be tan negative 1 of b, which is 1, over 1. Okay, tangent of 1 over 1, that's the same as, inverse tan of 1 over 1. Inverse tan of 1 over 1 is just inverse tan of 1. So that means my adjacent and my opposite have to be the same. So where does that happen? On my unit circle again, where does that happen? That happens when I have an isosceles right triangle. Okay, so this is my pi over 4. That happens at pi over 4. So again, using the unit circle, so my argument is going to be pi over 4. So being able to make your unit circle and being able to look at it quickly and figure out these tangents, where is the tangent equal to 1, is a handy thing to do. If you can't, you can always rely on your calculator, but then you're not going to have exact answers, and then things don't always work out so perfectly because you're not being exact. All right, so our argument is pi over 4. So therefore, c sub 2 is equal to square root of 2 cis pi over 4. So here I have expressed z1 and z2 in modulus argument form. There they are. Now I want to write down the modulus for w. So since we're dividing them, you just divide the moduluses. So since it's z1 over z2, the modulus of w, and this is the notation for modulus of w, okay, just like magnitude of w, the modulus is the same as the magnitude. I just take z1 divided by z2. So it's going to be 2 over the square root of 2. That is the modulus of w. Now, by expressing z1 and z2 in modulus argument form, which we already did, write down the argument of w. So the argument of w is pi over, we're not done. To get w, let's go ahead and finish it to get the argument. So w is equal to, like I said, we divide the moduluses, but we have to subtract the arguments. We're going to subtract our arguments. So pi over 3 minus pi over 4, I need to get a common denominator for that. So let's write that again. My common denominator is going to be 12. So 4 pi over 12 minus 3 pi over 12, because I multiplied this one by 4 over 4 and this one by 3 over 3. And so that's going to leave me with 4 minus 3 is 1. So I'm going to be left with 2 over root 2 cis of pi over 12. But the answer just asks for the argument. And the way the notation for argument is you say arg w is equal to pi over 12. So that's all they're asking for on here, is they're just asking for the argument. What's the argument? It would be pi over 12. So I suppose I showed more work than I needed to, but that's okay, whatever. All right, find the smallest positive integer value of n such that w to the n is a real number. So smallest positive integer, okay, so we're raising w to a power, and it has to be a positive integer. So the smallest it could be was 1, 2, 3, 4, 5. So let's think back to our other problems where we were graphing these with the argams. Oh my gosh, where are my papers? Oh, right there, right underneath me. So remember when we were graphing these, each time I raised my imaginary number to another power, it just kept rotating the same amount. So this one was pi over 3, cis pi over 3. So I was going pi over 3. And then when I raised it to another power, I went another pi over 3 and another pi over 3. So when I do this current one that we're in, don't you wish you were doing this work? Let's get that out of the way. I'm going to be rotating by pi over 12, okay? So I'm going to be rotating. Each time I raise it to another power, I'm going to be raising it by pi over 12. So here I am on my coordinate plane, my imaginary coordinate plane. So w to the 0 is just going to come out here, whatever. Here's w to the 0. It's going to be right here. It's going to be equal to 1. Let's call that 1. And then I'm going to rotate it by pi over 12 to get the next one. So the next one, pi over 12, is really skinny. So there's my pi over 12. And it's going to have, 2 over root 2, however long that is. 2 divided by root 2, okay? Then I would square that, but again, I would rotate by another pi over 12. And then the next one, I'm going to raise that to the, let's see, this was to the first, to the second, to the third. I would raise that to the third, however long that is. But I'm always going to rotate by pi over 12. So each one of these rotations is going to be pi over 12. Well, all of these endpoints are all going to be imaginary numbers because they all have a b component. So if we put it in rectangular form, they all have an x, they all have a real and an imaginary component. It has a real and an imaginary component, real, imaginary component. But once I rotate all the way over to here and I end up on here, then it's just only going to have a real part. It's not going to have an imaginary part. So for example, if I go back and find, where's the first one? This one. See this one, w to the fourth? W to the fourth? Notice that if I was to put this in rectangular form, that would just be negative 16 plus 0i. It has no imaginary part, so it's real. So when I rotate through and I end up back here, I no longer have an imaginary component. So it took me 1, 2, 3, 4 rotations to get there. Oh, look, w to the 4th. Took me 4 rotations to get there because I went pi over 4, pi over 4, pi over 4, pi over 4. So same idea over here. I'm rotating pi over 12, pi over 12. So how many of those is it going to take? And I think you can probably just tell me the answer. Oh, it's going to take 12. So n is going to have to be equal to 12. Okay, to make it a little more mathy and to actually write something down, to actually show some work on here, it's going to be a real number when my, my argument is equal to pi. Or rather, let's see, how do I want to say that? I wrote this down somewhere else. I want the number, okay, the exponent times my rotation. When I rotate it enough times that I'm at pi, then I will have a real number, okay? Because that will give me, if I have a rotation of pi, I'm starting here, I end up there. And so I'll be real again. So if I solve this for n, well, I'm going to multiply both sides of the equation by the reciprocal, 12 over pi, multiply by 12 over pi. The pi's cancel out, and I'm left with n equals 12. So here, you can just think about it. How many of these pi over 12s do I need to rotate my way over here? Because each time that I raise my w to a power, it's rotating pi over 12. It's rotating pi over 12. So how many until I get all the way back over, until I'm just a real number and I no longer have any imaginary component? It's going to take 12 of them. So n has to be 12. W to the 12th is the first time that I will have a real number. If I want to find the next one, we'll just keep going and then just keep going. And it won't be until I get all the way back here, which would be n to the 24th. It would take 12 more of those to get me back to this point back to this axis. Sorry about that. All right, that's it. That was problem 4. Sorry to take so long.